The story of electricity begins quietly, long before wires, engines, or glowing lamps. It begins with observation, with simple materials, with patient curiosity, directed toward the natural world. For most of human history, electricity was not a tool. It was not even a concept. It was a subtle behavior noticed in certain materials, appearing briefly and disappearing just as quickly. In the ancient Mediterranean world, thinkers sought patterns in nature. They studied water, stone, wind, and stars. Among them was Thales of Miletus, who lived around the 6th century BCE. He is often remembered for his ideas about geometry and cosmology, yet one small observation connects his name to the earliest recorded encounter with electricity. Thales noticed that when amber, a fossilized tree resin, was rubbed with cloth or fur, it gained the ability to attract light objects such as straw or feathers. The effect was gentle. The pieces would lift slightly and cling to the amber's surface. At the key, time, there was no theory to explain this attraction. There were no instruments to measure it. It was simply one more property of the material world. Amber was already valued for its color and warmth, and now it revealed another quiet behavior. The Greek word for amber, electron, would much later give rise to the term electricity, though that connection lay far in the future. For centuries, this phenomenon remained a curiosity rather than a subject of systematic study. Ancient scholars documented many natural effects, but the tools required for careful experimentation had not yet developed. The attraction produced by rubbed amber was subtle and fleeting. It did not produce light or heat in a sustained way. It could not be stored or directed. Without a framework to connect it to larger forces, it remained an isolated observation. Meanwhile, another electrical phenomenon occasionally illuminated the sky: lightning. Storms rolled across continents, releasing bright flashes and deep, rumbling sounds. Lightning was powerful and dangerous. It split trees, struck buildings, and ignited fires. Ancient cultures interpreted it through mythology and religion. It was associated with gods and divine anger. There was no reason at that time to connect the faint pull of rubbed amber with the violence of a thunderstorm. The two seemed entirely different in scale and character. The slow shift from observation to investigation began much later, during the Renaissance and early modern period. By the 16th and 17th centuries, natural philosophy had begun to emphasize measurement and repeatable experiments. Instruments were improving. Curiosity was turning toward controlled study rather than symbolic interpretation. In England, a physician and scholar named William Gilbert made an important contribution at the turn of the 17th century. Gilbert studied magnetism carefully. He distinguished between magnetic forces, such as those exhibited by lodestones, and the attractive force produced by rubbed amber. Through experimentation, he realized that several materials, when rubbed, could produce similar attractive effects. He referred to these materials as electric, deriving the term from the Greek word for amber. Gilbert's work marked a gradual shift in thinking. Electricity was no longer merely a property of amber. It was a broader category of behavior. He described how various substances could become electrically active after friction. He also observed that moisture could diminish this effect. These were careful, practical observations, recorded in a systematic way. The phenomenon was still understood only in qualitative terms, but it was beginning to take shape as a field of study. As the 17th century progressed, experimenters developed simple machines to generate static electricity. Rotating glass spheres or cylinders were rubbed by hand or by cloth. These devices could produce larger amounts of static charge than amber alone. Sparks could be seen in darkened rooms. Light cracking sounds accompanied the discharges. Observers noticed that charged objects could repel as well as attract each other. This was a crucial detail. It suggested that electricity was not a single, simple force, but something capable of interaction and balance. In the early 18th century, European scientists began to explore these behaviors more deliberately. They discovered that electricity could be transferred from one object to another. It could travel along certain materials more easily than others. Metals allowed the movement of electrical charge, while glass resisted it. Though the language of electrons and atomic structure was still far away, patterns were emerging. One important development during this period was the invention of the Leyden jar, a device capable of storing static electricity. Developed independently by experimenters in the Netherlands and Germany, the Leyden jar consisted of a glass container with metal foil on the inside and outside surfaces. When connected to a static generator, it could accumulate charge. When discharged, it released a noticeable spark. For the first time, electricity could be collected and held temporarily. This allowed for repeated experiments and more reliable observation. With the Leyden jar, electricity moved from fleeting curiosity to something closer to a controllable phenomenon. Demonstrations became popular in scientific societies and public lectures. Sparks were drawn from fingertips. Small shocks were delivered in chains of people holding hands. These displays were not theatrical in their scientific intention, though they often attracted attention. They revealed that electricity could move through bodies and across distances. In the American colonies, an interest in electricity grew as well. Among those drawn to its study was Benjamin Franklin. Franklin approached electricity with practical curiosity. Through a series of experiments in the mid-18th century, he proposed that electricity involved a single fluid that could exist in excess or deficiency. He described these conditions as positive and negative. Although his fluid model would later be replaced, his terminology of positive and negative charge remains in use. Franklin is often associated with a kite experiment conducted during a thunderstorm. The image of a key tied to a kite string has become part of popular memory. The purpose of the experiment was to test whether lightning and the smaller electrical sparks produced in laboratories were the same phenomenon. By drawing charge from a storm cloud using a conductive path, Franklin demonstrated that lightning was electrical in nature. The experiment was dangerous, and similar attempts in Europe resulted in fatal accidents. Yet the conclusion was clear. The force in the sky and the force in the laboratory were related. This recognition unified two previously separate observations: static electricity and lightning. The faint attraction of amber and the flash of a storm shared a common basis. Electricity was no longer confined to small tabletop devices. It was part of the atmosphere itself. By the late 18th century, scientists were seeking ways to generate electricity more reliably. Static machines produced brief discharges, but they could not provide a continuous flow. A major step occurred at the end of the century through the work of an Italian physicist, Alessandro Volta. Volta built what is now known as the voltaic pile, the first true battery. The voltaic pile consisted of alternating discs of zinc and copper, separated by pieces of cloth soaked in salt water. When stacked together, these layers produced a steady electrical current. Unlike static generators, which required friction and produced intermittent sparks, the battery provided a continuous flow of electricity. This was a quiet but decisive transformation. Electricity could now be studied as an ongoing current rather than a sudden discharge. Volta's invention opened new possibilities. Researchers could examine how electricity interacted with chemicals. They could observe how it traveled through wires. They could begin to quantify its strength and effects. The steady current allowed for more precise experiments, laying the groundwork for deeper understanding. As the 19th century began, electricity was transitioning from curiosity to science. It had moved from amber and storms into glass jars and metal stacks. The language describing it was becoming more structured. Terms such as charge, conductor, and circuit entered common use among researchers. Yet much remained unknown. The relationship between electricity and magnetism was still unclear. The underlying mechanisms were hidden within matter itself. The discovery of electricity was not a single moment. It was a gradual unfolding. Observations accumulated. Experiments refined earlier ideas. Each generation added detail and clarity. What began with a philosopher noticing the behavior of amber had evolved into a field of investigation supported by instruments and theory. The pace of discovery was steady. It required patience and repetition. It depended on the careful comparison of results. As the century continued, further connections would emerge, linking electricity to magnetism and eventually to light itself. But even before those revelations, the essential realization had taken root. Electricity was a natural force, present in materials and in the atmosphere, governed by consistent principles. It could be observed, measured, and increasingly directed. In this gradual way, through centuries of quiet inquiry, electricity shifted from mystery to subject. The sparks drawn in darkened rooms were no longer isolated curiosities. They were signs of a deeper structure within nature, waiting to be described with greater precision. During the early 19th century, the steady current provided by the voltaic pile allowed researchers to explore electricity in ways that had not been possible before. The flow from Volta's stacked metals could last for hours. It could be connected to wires. It could be directed through solutions and across small gaps. The spark was no longer the main object of study. The current itself became the focus. In 1800, shortly after learning of Volta's battery, two English chemists, William Nicholson and Anthony Carlisle, used a voltaic pile to pass electricity through water. They observed that bubbles formed at two separate wires placed in the liquid. The gas collected at one wire was hydrogen. At the other, oxygen appeared. Electricity was able to separate water into its components. This process came to be known as electrolysis. It revealed that electrical current could drive chemical change. The implications were quiet but profound. Electricity was not only a force of attraction or repulsion. It was connected to matter at a deeper level. Chemical bonds could be influenced by an invisible current. This suggested that electricity might be woven into the structure of atoms themselves, though the atomic model would develop much later. Over the next decades, many scientists repeated and refined these experiments. They measured how much material was produced during electrolysis. They examined how different substances responded to electrical flow. Patterns began to appear. Certain materials allowed current to pass easily. Others resisted it. The distinction between conductors and insulators became clearer through repeated observation. In 1820, an unexpected connection emerged. A Danish physicist, Hans Christian Ørsted, was lecturing about electricity when he noticed that a compass needle near a current-carrying wire deflected from its usual north-south alignment. The needle moved only while current flowed. When the circuit was broken, it returned to its original position. Electricity and magnetism, once studied separately, were interacting. Ørsted's observation was simple. It required careful attention rather than elaborate equipment. Yet it revealed a direct link between electrical current and magnetic force. This result was soon repeated across Europe. The relationship proved reliable. Electric currents produced magnetic effects. Shortly afterward, the French physicist André-Marie Ampère began to study this connection in a systematic way. He demonstrated that two parallel wires carrying current could attract or repel each other, depending on the direction of the currents. From these experiments, Ampère developed mathematical descriptions of the forces involved. He treated electricity and magnetism as aspects of a unified system. The idea of electromagnetism slowly took form. It was not announced with excitement. It grew through calculation and repetition. Each experiment added detail. Each measurement narrowed uncertainty. Electricity and magnetism were no longer independent curiosities. They were related expressions of a common, underlying phenomenon. In 1831, another important step occurred. The English scientist Michael Faraday explored whether magnetism could also produce electricity. He arranged coils of wire and moved magnets near them. When the magnetic field around a coil changed, he detected a current in the wire. The current did not require a battery. It was induced by motion and changing magnetic conditions. This process became known as electromagnetic induction. Faraday's work showed that electricity could be generated mechanically. Movement could create current. This principle would later allow the construction of generators and dynamos. At the time, it revealed a symmetry. Electricity could produce magnetism. Magnetism, when altered, could produce electricity. Faraday approached these experiments with patience. He relied less on mathematics and more on visualization and careful arrangement. He imagined lines of force extending through space. Though invisible, these lines helped him describe how fields behaved. His ideas influenced later theoretical work, even if the language he used was still evolving. By the mid-19th century, a clearer structure was emerging. Electric charge could exist in positive and negative forms. Current represented the flow of charge. Magnetic fields surrounded moving charges. Changing magnetic fields could generate current. These principles were tested repeatedly in laboratories across Europe. In Scotland, a physicist named James Clerk Maxwell worked to unify these findings mathematically. During the 1860s, Maxwell developed a set of equations describing how electric and magnetic fields interact. His equations showed that changes in electric fields create magnetic fields, and changes in magnetic fields create electric fields. Together, they form waves that travel through space. From Maxwell's calculations came a striking conclusion. The speed of these electromagnetic waves matched the measured speed of light. This suggested that light itself is an electromagnetic wave. Electricity, magnetism, and light were not separate forces. They were manifestations of a single, unified phenomenon. Maxwell's theory did not immediately transform daily life. It provided clarity and coherence. It showed that the behaviors observed since the days of amber and static sparks followed consistent laws. The invisible forces had mathematical form. They could be predicted and measured with precision. Meanwhile, practical applications were developing in parallel. The principles of induction were used to design electrical generators. Rotating coils within magnetic fields produced steady currents. These machines converted mechanical energy into electrical energy. Early generators were modest in scale. They powered laboratory experiments and small demonstrations. In the latter part of the 19th century, inventors refined these devices. Electrical lighting systems began to appear in cities. Wires carried current across streets. Power stations converted the motion of steam engines into electricity. These developments rested on the scientific foundations laid by earlier generations. Throughout this long progression, the discovery of electricity did not follow a single path. It unfolded gradually. Observation led to experiment. Experiment led to theory. Theory guided further observation. Each stage depended on careful measurement and repetition. By the end of the 19th century, electricity was no longer an unfamiliar force glimpsed in amber or storms. It was understood as a fundamental aspect of nature. It could be generated, transmitted, and transformed. Its behavior could be described in equations. Its effects could be harnessed in machines. Yet, even then, deeper layers remained to be explored. At the turn of the 20th century, studies of atomic structure revealed that electricity is tied to the presence of charged particles within matter. The electron was identified as a discrete carrier of negative charge. This discovery clarified the microscopic origin of electrical current. Charges moved through materials because tiny particles were shifting position. The earlier centuries of work made this understanding possible. Without the careful experiments of Gilbert, Franklin, Volta, Ørsted, Ampere, Faraday, and Maxwell, the electron would have remained an abstract concept. Their observations created a framework into which atomic theory could fit naturally. Looking back across the centuries, the path appears steady rather than sudden. A small attraction between amber and straw led to systematic study. Laboratory sparks suggested a link to lightning. Batteries enabled continuous currents. Currents revealed connections to magnetism. Magnetism led to induction. Induction supported generators. Mathematical insight unified the entire system. There was no single moment of invention. There was a long process of uncovering. Each generation saw a little more clearly than the one before. Knowledge accumulated quietly. Today, electricity flows through nearly every aspect of modern life. It powers communication, transportation, and illumination. Yet beneath these applications lies the same force once noticed in a piece of rubbed amber. The scale has changed. The understanding has deepened. The underlying phenomenon remains consistent. The discovery of electricity reflects the patient character of science. It required attention to subtle details. It required instruments that improved slowly over time. It required ideas that could be tested and revised. The force itself did not change. Human understanding did. In quiet laboratories, in lecture halls, and in open fields beneath storm clouds, observers watched, measured, and compared. Their work stretched across continents and generations. Each experiment was a small step. Each step connected to those before it. As the 19th century closed, the study of electricity had become a central part of physics. The field was mature in its basic principles. The language describing it was precise. The early questions about amber and lightning had grown into a comprehensive theory of electromagnetism. The light from electrical lamps glowed steadily in growing cities. Wires hummed softly overhead. The once mysterious spark had become part of daily routine. Yet its story still carried the memory of careful observation and slow understanding. From fossilized resin to rotating generators, from storm clouds to mathematical equations, the path of discovery unfolded gradually. It was shaped by curiosity rather than urgency. It advanced through patience. And in that steady movement, the quiet force within matter revealed itself, piece by piece, until it stood as one of the most carefully described aspects of the natural world. As the 19th century moved forward, the study of electricity shifted from large visible apparatus to smaller and more precise questions. Instruments improved. Measurements became finer. Researchers no longer focused only on sparks and coils. They began to ask what electricity truly was at the level of matter itself. In the late 19th century, experiments with gas discharge tubes offered new clues. When a high voltage was applied across electrodes sealed inside a glass tube containing low-pressure gas, a faint glow appeared. This glow seemed to originate from rays traveling from the negative electrode. These were called cathode rays. Their behavior was puzzling at first. They cast shadows. They could be deflected by magnetic fields. In 1897, the English physicist J.J. Thomson studied cathode rays carefully. By measuring how they bent in electric and magnetic fields, he determined that they consisted of particles. These particles carried negative charge. They were far smaller than atoms. Thomson had identified the electron. This discovery provided a physical carrier for electricity. Electrical current was not a mysterious fluid. It was the movement of charged particles in metals. Electrons drifted through a lattice of atoms. In solutions, charged ions moved instead. The idea of charge became anchored in tangible entities. Soon after, other experiments refined this picture. In 1909, the American physicist Robert A. Millikan measured the charge of the electron through his oil drop experiment. By balancing tiny charged droplets between electric plates, he determined the fundamental unit of charge. It was always the same quantity, Charge came in discrete amounts. It was quantized. This understanding brought calm clarity to earlier observations. The attraction and repulsion described centuries before could now be explained as interactions between charged particles. The continuous current from a battery was a steady movement of electrons. The magnetic fields around wires arose from those moving charges. During the same period, atomic theory advanced. In 1911, Ernest Rutherford proposed that atoms contain a dense central nucleus surrounded by electrons. Later, refinements described electrons as occupying probabilistic regions rather than fixed orbits. These developments placed electricity within the broader framework of atomic physics. Electrical behavior was inseparable from the structure of matter. In parallel, technological applications expanded quietly. Power generation became more efficient. Large turbines turned within magnetic fields, producing alternating current. The distribution of electricity over long distances required transformers, devices based on electromagnetic induction. These allowed voltage to be increased for transmission and decreased for safe use. Alternating current systems were refined by several engineers and inventors. Among them was Nikola Tesla, who developed practical methods for generating and transmitting alternating current. His work built upon Faraday's principles. It did not alter the fundamental understanding of electricity, but it demonstrated how deeply those principles could be applied. Electric, lighting, telegraphy, and later telephony relied on these steady currents. The telegraph had already shown in the mid-19th century that electrical signals could travel along wires over great distances. By the early 20th century, electrical networks had become common in industrialized regions. Wires stretched between cities. Power stations converted coal, water, or steam into electrical flow. Despite these visible changes in society, the scientific understanding of electricity continued to develop in a measured way. In the early 20th century, the field of quantum mechanics emerged. It described how electrons behave at very small scales. Rather than moving in simple, classical paths, electrons exhibited wave-like properties. Their positions and energies followed probabilistic rules. These ideas did not overturn earlier discoveries. They extended them. Classical electromagnetism remained accurate for large-scale phenomena. Quantum theory explained behavior within atoms and materials. Together, they formed a layered understanding. In the 1920s and 1930s, physicists refined the theory of how electrons move through solids. This led to solid-state physics. Researchers discovered that materials differ in their ability to conduct electricity because of their electronic structure. Metals have free electrons that move easily. Insulators do not. Semiconductors occupy a middle position. Their conductivity can be adjusted by small changes in composition. The development of semiconductors later enabled electronic devices such as transistors. In 1947, researchers at Bell Laboratories constructed the first practical transistor. It could amplify and switch electrical signals using the controlled movement of electrons within a semiconductor crystal. This device relied entirely on the accumulated understanding of electrical behavior at both classical and quantum levels. Although these developments shaped modern electronics, the underlying story remained steady. Electricity was still the movement of charge. Magnetic fields still arose from motion. light was still an electromagnetic wave. The deeper mathematics remained valid. Over time, the measurement of electrical quantities became standardized. Units such as the volt, named after Volta, and the ampere, named after Ampere, entered formal use. The coulomb measured charge. The ohm described resistance. These units provided consistency across experiments and applications. They reflected the gradual organization of knowledge into a coherent system. As the 20th century progressed, electricity became woven into nearly every area of life. Power grids expanded. Communication systems relied on electrical signals. Medical instruments used precise currents for diagnosis and imaging. Yet beneath these applications lay principles established through centuries of patient inquiry. The discovery of electricity, when viewed as a whole, reveals a pattern of accumulation rather than sudden insight. Ancient observers noticed small attractions. Early modern scientists distinguished materials and recorded behaviors. 18th century experimenters stored charge and compared lightning to sparks. 19th century researchers unified electricity and magnetism and described them mathematically. 20th century physicists located electricity within the structure of atoms. Each stage rested quietly upon the previous one. There were moments of clarity, but they emerged from sustained effort. No single figure completed the story. It unfolded across cultures and generations. In reflecting on this long progression, one can see how human understanding often develops. A natural phenomenon is observed. Language is formed to describe it. Instruments are built to measure it. Theories are proposed, tested, and refined. Over time, the phenomenon becomes familiar, even ordinary. Electricity today feels ordinary. Lights turn on without thought. Devices operate silently. Signals travel invisibly through cables and air. Yet this familiarity rests on a deep foundation. That foundation began with amber warmed by friction. It expanded through careful experiment. It matured through mathematics and measurement. The pace of discovery gradually slowed as principles solidified. New questions emerged at smaller scales, but the central structure remained stable. Electric and magnetic fields obey Maxwell's equations. Charges interact according to consistent laws. Energy flows through circuits in predictable ways. In laboratories and classrooms, these principles are now taught as part of basic science. Students repeat experiments that once revealed unknown territory. They charge rods with cloth. They observe compass needles near wires. They build simple circuits powered by batteries. These activities echo centuries of investigation. The arc of discovery feels complete in its broad outline. Electricity is understood as one aspect of the electromagnetic interaction, one of the fundamental forces of nature. Its behavior connects to atomic structure, to light, and to the transmission of energy. The journey from curiosity to comprehension did not rush. It unfolded in measured steps. Observation led to question. Question led to experiment. Experiment led to theory. Theory guided further exploration. The pattern repeated gently over time. Now, when electrical current moves through a conductor, it does so quietly, following principles long established. The force that once startled observers with a spark now hums softly in the background of daily life. And in tracing this history, one sees not a single invention, but a gradual revealing, a natural force present from the beginning, patiently observed and carefully understood. The light that electricity produces is steady. The understanding behind it is steady as well, and the story of its discovery rests in that calm persistence, unfolding slowly across the centuries until it became part of the quiet structure of the world. As understanding settled into clear mathematical form, electricity became part of a broader picture of nature. It was no longer studied in isolation. It stood beside mechanics, thermodynamics, and optics as one of the central domains of physics. Each field described patterns in the behavior of matter and energy. Electricity fit naturally among them. In the early 20th century, the relationship between electricity and energy became even more precise. When charges move through a circuit, energy is transferred. This transfer can appear as light, heat, motion, or chemical change. The conservation of energy applies without exception. Electrical energy is not created from nothing. It is converted from other forms, such as mechanical rotation in a generator or chemical reactions within a battery. This clarity allowed engineers to calculate systems carefully. Power could be measured in watts. Efficiency could be determined. Losses due to resistance could be anticipated. These calculations were not abstract. They guided the construction of power plants, transmission lines, and household circuits. The structure of electrical circuits also became more refined. A simple circuit contains a source of potential difference, conductive paths, and a load. The potential difference, often called voltage, provides the push that moves charge. Current describes the rate at which charge flows. Resistance determines how strongly a material opposes that flow. These relationships were summarized in what became known as Ohm's law, connecting voltage, current, and resistance in a simple, proportional form. Such principles are now introduced early in scientific education. Yet, they emerged slowly. They required careful measurement and agreement across laboratories. Instruments such as galvanometers, voltmeters, and ammeters improved gradually. Precision increased over decades rather than years. As measurement sharpened, so did theoretical understanding. Maxwell's equations, once expressed in complex mathematical notation, were reformulated in more compact vector form. They described electric fields, magnetic fields, charge density, and current density in a unified framework. These equations predicted not only light, but also radio waves. In the late 19th century, Heinrich Hertz experimentally confirmed the existence of electromagnetic waves beyond visible light. He generated and detected radio waves in his laboratory. The waves behaved exactly as Maxwell's equations predicted. They reflected and refracted. They traveled at the speed of light. This confirmation strengthened confidence in electromagnetic theory. It also opened the way to wireless communication. Though the practical applications would develop gradually, the scientific basis was clear. Electricity and magnetism formed a continuous spectrum of waves, extending beyond human vision. At the atomic level, the role of electrons became central. In metals, electrons occupy energy levels that allow them to move freely when an electric field is applied. In insulators, electrons are tightly bound to atoms. The difference lies in the arrangement of energy bands within the material. This band theory of solids explained conductivity with quiet precision. Semiconductors offered an intermediate case. Their conductivity could change with temperature or the introduction of small impurities. By carefully adding specific atoms to a semiconductor crystal, engineers could create regions with excess electrons or with missing electrons, called holes. The movement of electrons and holes under applied voltage formed the basis of diodes and transistors. These devices allowed electrical signals to be controlled in subtle ways. Amplification and switching became possible without mechanical parts. The change was gradual but transformative. Electronic circuits grew smaller and more reliable. Computation shifted from large electromechanical systems to compact, solid-state designs. Even as applications expanded, the underlying physics remained calm and consistent. Charges interacted through fields. Fields carried energy and momentum. The equations governing them did not change with scale. Whether in a small laboratory experiment or a continental power grid, the same principles applied. In the mid-20th century, quantum electrodynamics refined the description of how charged particles interact with electromagnetic fields. It combined quantum mechanics with special relativity. The theory predicted experimental results with remarkable accuracy. Yet for everyday electrical phenomena, classical electromagnetism remained sufficient. The deeper theory added resolution at very small scales, without disturbing established laws. Throughout these developments, the story of electricity retained its gradual character. It began with materials rubbed by hand. It continued through coils of wire and rotating magnets. It entered the structure of atoms and the behavior of subatomic particles. Each layer extended the one before. Modern electrical systems operate quietly. Power plants convert kinetic energy into current through turbines and generators. Transformers adjust voltage for efficient transmission. Substations distribute electricity through networks of conductors. In homes and workplaces, circuits divide power among lights, appliances, and devices. When a switch is closed, electrons begin to drift almost immediately. The signal travels at a large fraction of the speed of light, though the individual electrons move much more slowly. Energy flows through the electromagnetic field surrounding the conductors. These details are now well understood. They can be described precisely in textbooks and laboratories. Yet the familiarity of electricity can obscure its long history. The path from amber to electron was not direct. It curved through observation, speculation, correction, and refinement. It depended on tools as simple as cloth and resin, and as complex as particle accelerators. In quiet reflection, the discovery of electricity appears less like a sudden unveiling and more like a patient unveiling of layers. At first, only surface behavior was visible. Later, connections formed between seemingly separate phenomena. Eventually, a coherent framework emerged. The glow of a lamp, the hum of a transformer, the signal traveling through a cable, all rest upon this framework. The force that once surprised ancient observers now moves unnoticed in walls and beneath streets. Its behavior is predictable. Its laws are stable. The scientific understanding of electricity is not frozen. Research continues at smaller scales and higher energies. Yet the broad outline is settled. Charges exist. They interact through electric and magnetic fields. Those fields obey consistent equations. Energy is conserved. These statements remain firm. The long effort to understand electricity reflects a broader pattern in human inquiry. Nature presents subtle signs. Curiosity leads to careful study. Knowledge accumulates slowly. Over time, what was once mysterious becomes clear. And so the story continues in quiet laboratories and classrooms. Students repeat experiments that echo centuries past. They observe attraction and repulsion. They measure current and voltage. They trace field lines with iron filings. Each repetition carries forward a long tradition of steady learning. In this way, the discovery of electricity is less an event and more a continuum. It stretches from ancient curiosity to modern clarity. It moves without haste. As the understanding deepened, the tone of inquiry grew calmer. Questions that once seemed large found measured answers. Electricity became one more aspect of the natural order, integrated into the larger structure of physics. The light it produces is steady. The fields it forms are invisible, yet dependable. The charges move according to quiet rules, and beneath the layers of theory and application, the simple observation remains. A material rubbed by hand can attract a small piece of straw. From that small beginning, through centuries of patient thought, a comprehensive understanding emerged. The progression was gradual, the pace was measured, and the force itself remained constant, waiting to be observed, described, and gently understood. As the 20th century advanced, electricity became woven into the quiet infrastructure of daily life. Its presence was steady rather than noticeable. Homes were designed with wiring hidden inside walls. Power stations operated at a distance, often far from the cities they served. The physical principles behind these systems did not change. They were applied with increasing care and efficiency. The generation of electrical power followed a simple sequence. Mechanical energy turned a turbine. The turbine rotated a coil of wire within a magnetic field. According to the principle of electromagnetic induction, described by Faraday, a changing magnetic environment around the coil produced an electric current. This current flowed outward through conductors. The process was continuous as long as motion continued. Different energy sources could provide that motion. Flowing water turned hydroelectric turbines. Expanding steam from heated water rotated blades in thermal power plants. Later, nuclear reactions were used to heat water and produce steam, though the electrical generation itself remained the same. In every case, moving magnets and coils interacted in accordance with established laws. Transmission required attention to resistance. As current travels through a conductor, some energy is lost as heat. Increasing voltage while reducing current allows the same amount of power to be transmitted with less loss. Transformers, which operate through induction between coils, adjust voltage levels efficiently. These devices contain no moving parts. They rely entirely on alternating current and magnetic coupling. The organization of electrical grids demanded careful synchronization. In alternating current systems, voltage and current oscillate in cycles. Generators across a region must remain in phase with one another. Their frequencies must match precisely. Engineers developed methods to monitor and adjust these conditions. Stability became a matter of continuous measurement rather than guesswork. Meanwhile, at smaller scales, electronics continued to refine control over electric charge. Vacuum tubes had already demonstrated the ability to guide electrons through empty space within sealed glass envelopes. These tubes amplified signals in early radios and televisions. Later, semiconductor devices replaced them. Transistors operated through carefully structured materials, guiding electrons across junctions between differently doped regions. The invention of the integrated circuit in the mid-20th century allowed many transistors to be formed on a single piece of semiconductor. Electrical pathways were etched into silicon. Signals moved across microscopic distances. The principles governing their motion remained the same as those discovered in earlier centuries. Only the scale had shifted. Throughout these changes, measurement and standardization deepened understanding. The International System of Units formalized definitions of electrical quantities. Eventually, units such as the volt and the ohm were defined in terms of fundamental physical constants. This linked practical measurement to the deeper structure of nature. At the theoretical level, the electromagnetic force came to be described as one of four fundamental interactions, alongside gravity, the strong nuclear force, and the weak nuclear force. Within the framework of modern physics, electromagnetic interactions arise from the exchange of photons between charged particles. This description belongs to quantum field theory. It extends classical ideas without contradicting them. Despite the sophistication of these theories, the essential behavior of electricity remains accessible. A closed circuit allows charge to flow. An open circuit stops that flow. Materials differ in conductivity because of their atomic arrangement. Magnetic fields arise from moving charges. Changing magnetic fields induce currents. These relationships are consistent and reproducible. In classrooms, simple demonstrations still mirror ancient observations. A plastic rod rubbed with cloth attracts small pieces of paper. A simple battery lights a small bulb. A compass needle responds to a nearby wire carrying current. These experiments reflect centuries of accumulated knowledge, yet they require little equipment. The underlying force is direct. The discovery of electricity can therefore be understood as layered understanding rather than invention. At first, its presence was noticed in isolated behaviors. Later, patterns were identified. After that, mathematical descriptions unified the patterns. Eventually, microscopic explanations connected those descriptions to atomic structure. Each layer did not replace the one before. It clarified it. The attraction of amber is now explained in terms of electron transfer between materials. The spark is understood as a rapid equalization of charge across a gap. Lightning is seen as a large-scale electrical discharge within the atmosphere, driven by charge separation in storm clouds. The scale differs, but the principles remain. Over time, electricity moved from curiosity to necessity. Yet, even as reliance increased, its study grew quieter. The central questions had been answered. Research shifted towards specialized topics, such as superconductivity, plasma physics, and quantum information. These areas extend the understanding of electric and magnetic behavior under specific conditions. They do not alter the fundamental story. Superconductivity, for example, describes a state in which certain materials conduct. electricity with no resistance when cooled below a critical temperature. The phenomenon arises from quantum mechanical pairing of electrons. Though unusual, it still follows the laws of electromagnetism. The absence of resistance reflects changes in how electrons interact within the material. In plasma physics, charged particles move freely in ionized gases. Electric and magnetic fields guide their motion. Such plasmas occur in stars, including the Sun, and in controlled laboratory devices. Once again, the same principles apply at larger scales. The arc of discovery grows calmer as it approaches the present. The questions become more precise, the tools become more refined. Yet the foundational structure remains unchanged from the framework established in the 19th century. Looking back across the centuries, one sees continuity. Ancient thinkers observed attraction. Early modern experimenters named and categorized it. Enlightenment scientists stored and compared it. 19th century physicists unified it with magnetism and light. 20th century researchers located it within the atom, each stage connected gently to the next. Electricity did not reveal itself all at once. It unfolded gradually, responding to steady curiosity. Its laws were not imposed by human invention. They were uncovered through observation and careful reasoning. Now, in the quiet background of modern life, electrical currents flow through conductors without drawing attention. Signals move through optical fibers and wireless fields. Devices operate through patterns of charge and field shaped by design. The force itself remains unchanged from the time when amber first attracted straw. The story of electricity is therefore a story of patience. It is a record of small steps taken over long periods. It shows how persistent observation can transform mystery into understanding. In the steady hum of a power line, one can sense the continuity of this history. The motion of electrons today follows the same principles described by Maxwell. The generation of current still relies on Faraday's induction. The naming of units recalls Volta and ampere. The terminology of positive and negative traces back to Franklin. These connections are not dramatic. They are quiet reminders of continuity. The thread stretches unbroken from ancient curiosity to modern infrastructure. As the narrative slows, it becomes clear that electricity was always present. Humans did not create it. They learned to see it, then to describe it, and finally to guide it with care. The gradual unveiling of this force reflects a broader rhythm within science. Knowledge accumulates through attention, patterns emerge through repetition, explanations settle into place over time. And so the light that glows in a room, the signal that moves across distance, and the quiet field surrounding every charge all share a common origin in centuries of steady inquiry. The discovery continues, not in the sense of finding a new force, but in refining understanding. Yet, the main path has been traced. The outline is complete. Electricity rests now within the calm structure of physical law, understood, measured, and gently applied. With the broad framework of electromagnetism in place, later generations turned their attention to refinement rather than discovery. The questions became narrower, the measurements became more exact, the central ideas remained steady. One area of quiet progress involved the precise measurement of electrical standards. Over time, scientists sought to define units such as the volt and the ampere in terms of universal constants rather than physical objects. This ensured that measurements would be consistent across countries and laboratories. Electrical metrology became a careful discipline of comparison and calibration. The Josephson effect and the quantum Hall effect provided stable references for voltage and resistance. These phenomena arise from quantum behavior in materials under specific conditions. Though subtle, they allowed electrical units to be anchored to fundamental constants of nature. In this way, the study of electricity returned again to the atomic scale, closing a long circle from amber to quantum precision. At the same time, electrical theory found harmony with relativity. Maxwell's equations had already implied that the speed of electromagnetic waves was constant. This insight influenced the development of special relativity in the early 20th century. Electric and magnetic fields transform into one another depending on the motion of the observer. They are different aspects of a single electromagnetic field. This conceptual unity did not disturb practical applications. Circuits continued to operate as before. Generators continued to turn. Yet the theoretical view grew more cohesive. Electricity became part of a larger geometric structure describing space and time. In laboratories studying particle physics, high-energy experiments revealed that electric charge is conserved in all observed interactions. No process has ever been observed that creates or destroys net charge. This conservation law stands alongside conservation of energy and momentum. It reinforces the stability of electromagnetic theory. On a more everyday scale, the understanding of materials deepened further. Researchers learned how impurities, temperature, and structure influence conductivity. The behavior of electrons in crystalline solids could be described using quantum mechanics and statistical physics. Band gaps explained why some materials conduct and others do not. The distinction between metals, semiconductors, and insulators became a matter of energy levels rather than simple classification. In semiconductors, small adjustments in composition allow precise control of electrical properties. This made possible the development of microprocessors and memory devices. Billions of transistors now operate within a single integrated circuit. Each transistor guides the flow of electrons through a controlled region. Though the scale is microscopic, the governing laws remain those first unified in the 19th century. The spread of electrical technology across the world was gradual. Rural electrification projects extended power lines to remote regions. Renewable energy sources such as wind and solar were incorporated into electrical grids. Solar cells, in particular, rely on the photoelectric effect, in which light striking a material frees electrons and generates current. This effect was explained in the early 20th century through quantum theory, complementing classical electromagnetism. Even here, the connection to earlier discoveries is clear. Light, understood as an electromagnetic wave, interacts with matter at the level of electrons. The movement of those electrons becomes usable current. The cycle of understanding remains continuous. In modern communication systems, electrical signals often travel as modulated electromagnetic waves through space or optical fibers. The underlying principle is unchanged. Oscillating electric and magnetic fields propagate at finite speed. Information is encoded in their amplitude, frequency, or phase. Receivers detect these variations and convert them back into electrical currents. Despite the complexity of these systems, their foundations are simple. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. Charges respond to fields. Energy moves through space carried by these interactions. In recent decades, research into superconductivity and quantum coherence has explored conditions in which electrical resistance disappears or currents flow without energy loss. These states occur at very low temperatures. They reveal subtle collective behavior among electrons. Yet even these unusual phenomena remain consistent with electromagnetic theory. As knowledge accumulated, the tone of inquiry became quieter. The large conceptual shifts had already occurred. What remained was careful elaboration. Precision replaced speculation. Refinement replaced surprise. Electricity, once mysterious, is now described in textbooks with calm clarity. Its equations fit within a larger theoretical framework. Its units are defined by constants. Its behavior is predictable across scales, from atomic distances to planetary magnetic fields. Looking back over the entire span of discovery, one sees a steady rhythm. The earliest observers noticed attraction after friction. Centuries later, experimenters generated sparks in controlled settings. Batteries provided continuous flow. Induction linked electricity and magnetism. Mathematical theory unified them. Atomic physics located charge within matter. Quantum theory refined the picture. None of these steps erased the earlier ones. They layered upon them. The simple observation of rubbed amber remains correct. It is now explained in greater detail, but the phenomenon is unchanged. In the present day, electricity is rarely contemplated in isolation. It forms part of a broader understanding of energy and interaction. It supports communication, industry, medicine, and research. Yet its story is not one of invention in the usual sense. It is a story of recognition. The force existed long before humans observed it. Lightning struck long before language described it. Charged particles moved within atoms long before instruments detected them. Discovery consisted of learning to see what was already there. This gradual unveiling required patience. It required careful attention to small details. It required collaboration across centuries. Each generation inherited partial understanding and extended it slightly. Now, as electrical systems operate quietly across the globe, the sense of mystery has softened. The spark has become steady current. The storm has become equation. The amber has become electron. The path from curiosity to comprehension feels complete in its broad outline. Further research continues, but the central framework stands firm. And so the story of electricity settles into calm continuity, a natural force present in every atom, gently revealed through observation, experiment, and thought. Its discovery was not a single moment of insight. It was a long, measured unfolding. As the narrative approaches the present, the movement of electricity feels almost effortless. It flows through established systems, guided by principles that are now stable and well-tested. The sense of discovery has given way to quiet familiarity. In homes, current travels through copper conductors, arranged in simple loops. A potential difference, supplied by a distant generator, pushes electrons into motion. Switches interrupt or complete these loops. Devices convert electrical energy into other forms. A filament glows. A motor turns. A circuit processes information. The processes differ in detail, but each follows the same foundational rules. The motion of electrons in a wire is slow when considered individually. They drift under the influence of an electric field. Yet the energy transfer occurs much faster, carried by the electromagnetic field surrounding the conductor. This distinction between particle motion and energy flow is subtle, but it clarifies how circuits respond almost immediately when closed. In large transmission lines, alternating current oscillates at a fixed frequency, often 50 or 60 cycles per second depending on the region. This oscillation allows transformers to function. It also creates alternating magnetic fields that accompany the electric fields in space around the wires. The behavior is steady and predictable. Electrical safety, too, reflects accumulated understanding. Grounding provides a path for excess charge to disperse safely into the earth. Insulation prevents unintended contact. Circuit breakers interrupt flow when current exceeds safe limits. Each of these measures rests on knowledge of how charge moves and how materials respond. In scientific research, electricity remains a tool as much as a subject. Particle accelerators use electric fields to guide and accelerate charged particles. Microscopes rely on electron beams to reveal fine structures. Sensors detect faint electrical signals within biological tissues. The nervous system itself operates through controlled changes in electrical potential across cell membranes. These biological currents are small, but they obey the same principles described in physics. In the atmosphere, lightning continues to occur as it always has. Charge separation within storm clouds leads to electrical discharge. The scale is larger than laboratory sparks, yet the mechanism is similar. Air becomes ionized. A conductive path forms. Charge equalizes rapidly. The flash is bright, but the underlying process is consistent with known laws. Even on planetary scales, electric and magnetic fields interact. The Earth possesses a magnetic field generated by motion within its molten core. Charged particles from the Sun interact with this field, producing auroras near the poles. These luminous displays arise from electrons guided by magnetic lines of force colliding with atmospheric gases. Once again, familiar principles apply. As understanding matured, the need for dramatic explanation diminished. Electricity no longer appeared as an unpredictable force. It became a component of a larger system governed by symmetry and conservation laws. Modern textbooks present electromagnetism as a coherent subject. Students learn about fields, potentials, and waves. They solve equations that describe how charges interact. The problems are structured. The answers follow from established relationships. The once surprising behavior of static attraction is now a simple example in an introductory chapter. The language used to describe electricity has also stabilized. Terms such as field, charge, potential, and current carry precise meanings. They connect theory to experiment. They allow communication across languages and cultures. This shared vocabulary developed gradually, shaped by centuries of refinement. At this stage in the story, there are few broad questions remaining about the nature of electricity itself. The electromagnetic interaction is integrated into the standard model of particle physics. Its mathematical form is well defined. Its predictions match observation with high precision. Research continues at the boundaries, exploring extreme conditions and subtle effects. Yet the central framework remains unchanged from the structure built in the 19th century and refined in the 20th. Looking back once more to the beginning, the path appears long but continuous. The simple observation of attraction between amber and straw was the first step. It required nothing more than attention. From that moment, curiosity led to experimentation. Experimentation led to classification. Classification led to theory. Theory guided application. The force itself did not evolve. Human understanding did. Each layer of insight made the next possible. Without the naming of electric materials, there could have been no careful distinction between electric and magnetic effects. Without batteries, there could have been no steady currents. Without induction, there could have been generators. Without Maxwell's equations, there could have been no unification with light. The discovery of electricity, then, was not a conquest. It was a gradual recognition. It unfolded at a pace shaped by available tools and methods. It required patience more than brilliance. It depended on steady observation. Today, electricity surrounds us in quiet ways. It powers devices that rarely draw attention to the principles beneath them. The wires in walls remain unseen. The currents within circuits remain invisible. The fields in space cannot be felt directly, yet their presence is constant. In reflecting on this history, one can sense a gentle continuity between past and present. The same electrons that moved in early experiments move now in complex networks. The same equations that described sparks describe radio waves and light. The scale has changed. The understanding has deepened. The underlying order remains. As the narrative slows further, the discovery of electricity appears less like a sequence of events and more like a steady unveiling of structure. A natural force was observed. It was named. It was measured. It was described. It was applied. The movement from mystery to familiarity was gradual. It followed the rhythm of careful science. It required generations willing to ask simple questions and accept measured answers. And so the story settles into calm reflection. Electricity was never invented. It was found, piece by piece, within the ordinary materials of the world. Its quiet laws continue to operate, whether noticed or not. In the present day, the study of electricity continues, though it rarely carries the sense of novelty it once did. The broad principles are established. The equations are stable. The units are defined in relation to fundamental constants. What remains is refinement, extension, and careful application. Electrical power systems now interconnect across large regions. Grids balance supply and demand through continuous monitoring. Sensors measure frequency and voltage in real time. Small adjustments are made quietly to maintain stability. The behavior of current in these networks follows the same. Relationships described more than a century ago. Renewable energy sources have become more common. Wind turbines rotate in steady air currents. Solar panels convert sunlight into electrical current through the photoelectric effect. In both cases, electric charge moves in response to well-understood interactions. The methods differ from steam-driven turbines, yet the electromagnetic principles remain unchanged. Energy storage has also developed further. Modern batteries rely on controlled chemical reactions that separate and recombine charges. Lithium-ion cells, for example, move ions between electrodes during charging and discharging. The flow of electrons through the external circuit provides usable current. These processes are guided by electrochemistry, itself rooted in the early experiments of electrolysis. On smaller scales, electronic components have grown more compact. Transistors now measure only a few nanometers in size. Their operation still depends on the manipulation of electric fields within semiconductor materials. Quantum effects become more noticeable at these dimensions, yet engineers account for them with established theory. Communication technologies rely on electromagnetic waves traveling through air, vacuum, or fiber. Signals are encoded as variations in amplitude, frequency, or phase. Receivers interpret these variations and convert them back into electrical currents. The speed of propagation remains constant in vacuum, as described by Maxwell's equations and confirmed repeatedly. In laboratories, researchers explore materials that conduct electricity under unusual conditions. Some materials exhibit superconductivity at higher temperatures than previously known. Others display novel electronic properties due to their structure at the atomic level. These studies refine understanding without altering the central framework. In medicine, controlled electrical signals monitor and influence biological systems. Electrocardiograms measure the electrical activity of the heart. Deep brain stimulators deliver precise currents to targeted regions. These applications rely on the predictable behavior of charge in conductive tissues. Space exploration also depends on electrical systems. Solar panels power satellites. Electric propulsion systems accelerate ions to generate gentle thrust. Communication between spacecraft and Earth travels through electromagnetic waves across vast distances. The same laws apply beyond the atmosphere as within it. Through all these developments, the narrative of discovery has settled into continuity. There is no single turning point marking the completion of understanding. Instead, there is a steady confidence in principles that have been tested across scales and contexts. The conservation of charge remains unbroken. Electric and magnetic fields remain linked aspects of one interaction. Light remains an electromagnetic wave. These statements are not provisional in the broad sense. They are supported by extensive evidence gathered over generations. When students today learn about electricity, they often begin with static charge and simple circuits. They may rub a balloon against fabric and observe attraction. In that small experiment, they repeat a gesture performed thousands of years ago. The explanation now includes electrons transferring between materials, but the observation itself is unchanged. This continuity is quiet. It does not demand attention. Electricity has become part of the assumed background of modern life. Lights illuminate rooms without ceremony. Devices connect across continents without visible motion. The forces involved operate without sound or color. Yet beneath this familiarity lies the long path of understanding. From amber in ancient hands to semiconductor wafers etched with microscopic circuits, the journey has been gradual. Each century added clarity. Each experiment removed uncertainty. No single mind grasped the whole at once. Knowledge passed from one generation to the next. Errors were corrected, measurements improved, theories were revised and strengthened. Over time, the outlines sharpened until electricity stood as a well-described aspect of nature. Today, research continues in fields such as quantum information and advanced materials. Scientists explore how electrical states can encode data in delicate quantum systems. They study how charge behaves in two-dimensional materials only atoms thick. These inquiries extend the story gently forward. They do not disturb its foundation. Looking back across the full arc of history, the discovery of electricity appears as a patient unfolding rather than a sudden revelation. It began with a small attraction between objects. It progressed through careful naming and classification. It deepened with batteries and induction. It unified with magnetism and light. It settled into atomic theory and quantum description. The force itself never changed. It waited to be observed. It responded consistently to careful questioning. Human understanding approached it step by step, without haste. Now, in the quiet present, electricity flows through circuits with calm regularity. Its behavior can be calculated before a wire is even placed. Its presence can be measured with instruments of great sensitivity. Its principles are taught as part of basic scientific literacy. The light in a room is steady. The signal in a cable is steady. The fields surrounding every charge are steady. And so the story comes to rest in that steadiness. Electricity was not invented. It was uncovered layer by layer through centuries of observation and thought. From the warmth of rubbed amber to the precision of quantum standards. The path has been long and measured. The journey reflects a simple pattern. Notice what is there. Ask careful questions. Test the answers. Refine them slowly. In that quiet rhythm, a natural force became understood, and it continues quietly wherever charge moves and fields extend through space.